Hey friends, welcome. Today we are going to discuss the BET theory of multi-layer adsorption. When we are discussing the Langmuir theory of adsorption, this Langmuir theory, it is restricted only to the formation of monolayer of gas on any solid surface, and it disregards any possibility of formation of multi-layer. So in case of Langmuir adsorption isotherm, it is assumed that only a monolayer of the adsorbed gas on any solid surface will take place, and the multi absorption or multi-layered adsorption will not take place. But this is not the case, and in 1938 three scientists, namely BRUNAUER, that is B comes from BRUNAUER, E comes from EMMETT, and T comes from Taylor. So this three scientists in 1938, taking the basis of the Langmuir theory, they derived the expression which is popularly known as the BET theory, which explains the multi-layered adsorption phenomenon. So this theory is based on few assumptions. Amongst them, the first assumption is that the solid surface, it possesses the uniform localized site, and the adsorption at one site, it is not affected by the adsorption of the neighboring site. So any one molecule which is absorbed at a particular site will not be affected by the other neighboring site, as this was assumed in Langmuir theory. Also, further it is assumed that the layers, that is second, third and nth layer of the surface area available for the nth layer will be equal to the n minus first layer. So the surface area available for say first layer is the total amount of sites which are available on the surface. Then the surface area of available for the second layer will be equal to the amount of the surface area of the first layer. Then for second layer it will be the amount of surface area of the second layer. For third layer it will be the amount of surface area of the second layer, and for fourth it is the amount of surface area for the third, and so on. So in this way, on top of first layer, second layer will be formed, on top of second layer, third layer will be formed, and on top of third layer, fourth layer will be formed. And in this way, the physical adsorption of any gas molecule on the substrate will take place, and the energy of adsorption between the first layer and the adsorbent, it is constant, and it is assumed to be E1, and the succeeding layers, that is second layer, third layer and fourth layer, all the energy of adsorption, it is considered as same, and it is represented as EL, which is considered as the heat of liquefaction of the gas. Okay, so these are some of the assumptions on which the BET theory is based, and we will start with the derivation of BET theory. So suppose if we consider that A is our gas molecule, okay, and that gas molecule is being adsorbed on the substrate S, or it is being adsorbed on a substrate having S amount of vacant site, then we can write it will form AS, where AS is represents the adsorbed molecule on the vacant sites, or adsorbed molecule on the sites, and the rate constant K or K1 for the first adsorption or the first layer of adsorption, we can write it as it is equal to concentration of product divided by concentration of reactant. So I can write AS and concentration of A into concentration of S. Now over here, concentration of A, it is directly proportional to the pressure of gas. So we can write that concentration of A, it is directly, or it is equal to the pressure of P, pressure of the gas, and concentration of S, that is concentration of the vacant site, we can write it equal to theta V, which is the fraction of the sites or fraction of the vacant site, and concentration of AS, I can write it equal to theta 1, where theta 1 is the fraction of the sites which is covered by our single molecule. So for the first case, what will happen that we are having a surface, and on that surface several molecules are adsorbed. So the concentration of our gas will be proportional or will be equal to the pressure. The concentration of our sites or the amount of sites will be equal to the total amount of the vacant sites, that is fraction of vacant site, and concentration of AS will be equal to it is equal to the fraction of our sites which are covered by the molecule. So I can write K1, it is equal to theta 1 upon theta V into P. Okay, so this is for the first layer. Now similarly, from on the first layer, then second layer will sit, on the second layer third layer will sit, and on third layer fourth layer will sit. So similarly for the successive layers, that is for second, third and fourth layer, that is for successive layer, I can write AG plus again AS. So this AS will be now amount of the sites available, and then I can write it A2S, and this I can write it as K2 is equal to, I can write theta 2 upon, I can write theta 1 into P. So this will be the equilibrium constant for our second layer. Similarly, I will have gas plus I will have A2S, then I can write A3S, and similarly K3, it will be theta 3 upon theta 2 by P. Okay, because each layers are sitting on the successive layers, and hence the total area, that is for theta as we are taking theta V, so total area will be equal to the amount or area covered by the successive layer. And similarly for the ith layer, n-1s, so that is for nth layer, I will have ANS, and that will be equal to Kn, and that I can write it equal to theta n upon theta n-1 into P. So this will be the rate equations for the successive layers after the first layer. As we have discussed in the postulate, that the interaction between the adsorbed surface and the first layer will be unique, and the adsorption from second to third, third to fourth, fourth to fifth, and so on will be not very different, or they will be almost similar as two liquid molecules are interacting, and hence in such case the equilibrium constant for second, third, fourth and successive layers will almost be equal, and thus I can write that thus from assumption of EMMETT theory we can write that K2 is almost equivalent to K3, it is almost equivalent to K4, it is almost equivalent to Kn, and that I can write it equal to K, where K is the equilibrium constant for the liquefaction reaction, that is equilibrium constant for Kg, which is converted, or our gas molecule is converted into liquid. And whenever gas molecule is converted into liquid, the rate K, we can write it as it is equal to 1 upon P0, where P0 is the equilibrium vapor pressure of liquid. So this is the value of K. Now further we can use the equilibrium condition to generalize the fraction of absorption, that is we can rearrange all this expression in the form of the fraction of the molecules that are absorbed. So theta 2 equal to, so in place of all this we are substituting K, so this will be theta 2 is equal to K theta 1 into P. Similarly theta 3 will be equal to theta 2 into K into P, and so on. And when we combine these two expressions, that is we can substitute the value of theta 2 in this expression, so our theta 3 will be equal to theta 1 into Kp square. Similarly we will have theta 4 equal to, so again when we substitute the value of theta 3 in theta 4, we will have theta 1 into Kp cube, and so on we will get our values. Okay, so we can generalize, or we can repeat this operation, and we can generalize our expression in the form that is theta I is equal to theta 1 into Kp raised to I minus 1, because as we have theta 3 here, then we will have 2, so theta 4 it is cube, theta 5 it will be raised to the 4 raised to the power 4, and so on. So we can generalize it as theta I is equal to theta 1 into Kp raised to I minus 1. further when we will sum all the fractions, then sum of all the fractions will be unity, because as we are considering that our total surface is unity, and hence we can write unity 1 is equal to theta v, that is the amount of vacant sites, plus summation of I is equal to 1 to theta I. So theta I represents the all the amount of all the fraction of the adsorbed gas on the surface, and hence I can write this is equal to theta v plus summation of I theta 1 kp raised to I minus 1. Now suppose if we consider that value of kp, we are taking x. Okay, so in place of kp we will substitute x. So and when we will expand, we will have 1 is equal to theta v plus theta 1 into 1, that is something to the power 0 is 1, plus x square plus x cube, and so on. Okay, and assuming that n tends to infinity, that is we are having an infinite adsorption, then this is simply the expansion of one of the power series, and that power series is 1 upon 1 minus x. So 1 upon expansion of this power series, that is 1 upon 1 minus x, is this term. So in place of this value we can directly substitute 1 upon 1 minus x, and hence our value, that is 1, it will be equal to theta v plus theta 1 upon 1 minus x. So this is the value. Now further using the equilibrium condition for the first adsorption, so the equilibrium condition for the first adsorption, that was we had theta v is equal to theta 1 upon k1 into p. So we can rearrange in this form, that is theta v is equal to theta 1 upon k1 upon p, and further we can define a new constant, that is c, and this new constant is k1 upon k. Okay, so in order to convert this k1 in the form of c, we can divide and multiply by k. So we will have theta, or I can write it over here. So we will have theta v is equal to theta 1 upon k1 into p upon k, and then into k. So this will be c, and hence I can write theta 1 upon c into k into p, and k into p we know it is x. So I can write theta 1 upon c x. So theta v I got equal to theta 1 upon cx. So we can substitute the value of theta v in this expression, and hence we will have 1 is equal to, and theta 1 I can take common out. So theta 1 into 1 upon cx plus 1 upon 1 minus x, and further I can take the denominator common, and then I can rearrange this expression. So when I will take denominator common and rearrange this expression, I will have theta 1 will be equal to cx into 1 minus x upon 1 minus x plus cx. So cx into 1 minus x upon, I can take 1, and then plus c I can take common, so into x into c minus 1. So this will be the expression that I am left with for theta 1. Now this expression for theta 1 we will use in the later part of our derivation. Now further, suppose if we further consider that n are the total number of molecules that are adsorbed per unit mass of adsorbent, that is we are having certain amount of adsorbent, and on that, or a unit mass of an adsorbent, and for a unit mass of an adsorbent, n are the amount of the molecules, or the n are the amount of the gas molecules that are adsorbed per unit mass. And if we consider that Cs is the total amount of the sites which are present per unit mass, so n are the number of adsorbent, and Cs it is the amount of sites which are present per unit mass. So for the total number, that is for the first layer, for second layer, for third layer, the total number of sites which are carrying the molecule, we can write it in the terms of Cs into theta 1 will be the number of sites carrying one molecule or first layer of the molecule. Similarly, Cs into theta 2 will be the number of sites carrying two molecule, and so on accordingly. So hence the total number n, we can write it as n is equal to Cs into theta 1 plus 2 into theta 2 plus 3 into theta 3. So this will give us the total amount of total number of molecules, and Cs into theta 1 will give us the total amount of molecules which are present on our first layer. Cs into theta 2 will, or Cs into 2 theta 2 will give us the total amount of molecules which are present in second layer, third layer, and so on. And hence this I can write it as Cs into summation of I into theta I will give us the total number of molecule. And further we have seen the value of theta I, that is theta I, it was equal to theta 1 into x raised to I minus 1. So this theta I we have already seen, so we can substitute this value of theta I in this expression, and hence the total number of molecule I can write it as Cs into theta 1 into summation of I into x raised to I minus 1, and the expansion we'll get is Cs into theta 1 into 1 plus 2x plus 3x square and so on. Now this series, that is this series, is again the derivative of the first series that we have seen. How it is derivative, that let us see, that is 1 plus 2x plus 3x square plus so on. So when we differentiate this particular series, that is when we differentiate it, we will have, or the derivative series I can write it as ddx of 1 plus x square plus x plus x square plus x cube plus so on. Okay, and this we know it is ddx of 1 upon 1 minus x, and differentiation of this will be 1 upon 1 minus x square. Okay, so for this particular series, that is this particular series, we can substitute this particular value or this particular exponential form, and hence the total number of molecule n, it will be equal to Cs into theta 1 upon 1 minus x square. Okay, so this is the expression for total number of molecule, and if the entire surface is covered by monolayer, that is suppose we are having an adsorbent, and if entire surface or entire unit surface is covered by monolayer, then at that time n total number of molecule on monolayer will be equal to Cs, where Cs we know it is the total number of the surface site per unit mass. So the total number of molecule will be equal to the total number of sites. So suppose if you are considering that whole surface is covered by monolayer, then under such circumstances n mono, which represents the number of molecule on monolayer, will be equal to the total number of the surface sites, and hence in place of Cs we can substitute Nm, where Nm is the total number of molecules or all the molecules which are covering the monolayer into theta 1 upon 1 minus x square. Okay, now further we had the value of theta 1, which is theta 1 is equal to this particular value. So this value of theta 1 we will substitute in our expression, that is this particular expression, and hence we will have Nm into Cx upon, we will have 1 minus x in the numerator and 1 minus x square in the denominator. So we are left with 1 minus x into 1 plus C minus 1 into x. So this is the expression, or this expression gives the total number of molecule. So over here n, it represents, this expression represents the total number of molecules which are adsorbed on any gas surface, and generally for a gaseous system we are carrying out our measurement at standard temperature and pressure. So whenever measurement is carried out at standard temperature and pressure, the number of molecules are directly proportional to the volume. So hence in place of number of molecules, we can replace number of molecules by the respective volume, and hence we can write V total, which gives the total volume, is equal to, I can write Vm into Cx upon 1 minus x into 1 plus C minus 1x. Okay, so we are replacing in place of number of molecules volume, as the calculation is carried out at standard temperature and pressure, and at standard temperature and pressure, or at STP, the number of molecule is directly proportional to the volume, or it is equal to volume, and where V TOT is our total volume and Vm is the volume of the monolayer. Now further we have considered that X was equal to Kp and K is equal to 1 upon P0. So our X will be equal to P upon P0, where P is the pressure of the gas and P0 is the equilibrium pressure. So in place of X we can substitute P upon P0, and similarly we will have Vm into C, we will have P upon P0 upon this P upon P0. So I can write directly P0 minus P upon P0. So P0 in the denominator and P0 in the numerator, we can cancel it out directly into, we will have 1 plus C minus 1 P upon P0. So this gives the total volume of the molecule which are present. V total, it gives the total volume of the gas which is present, which is adsorbed on the surface, and this total volume is measured as a function of pressure P. Okay, it is measured as a function of pressure P, and further, if the equilibrium pressure, that is P0, it is equal, or if P0 is equal to P, that is pressure of gas, then this term will be equal to 0, and under such circumstances V will tend to infinity, because P0 minus P will be 0 and something upon 0 is infinity. So V will tend to infinity, that is singularity, or that is the equation. This equation has a singularity, and this will account for a steep increase in the isotherm. That is, suppose if we are looking at the isotherm, that is, if this is our mass and this is P upon P0, then there will be a sudden increase in the isotherm observed, and this sudden increase in the isotherm is basically because of P0, that is equilibrium pressure, is becoming equal to our pressure of the gas. Now further we can again rearrange this expression in order to obtain the BET isotherm, and we can rearrange this expression by take this term on right hand side, and this pressure term we can take in the denominator. So we will have V into P0 minus P upon P, that is equal to Vm into C upon 1 plus C minus 1 P upon P0. And further we can take reciprocal of this expression. So when we take reciprocal of this expression, we will have P upon V into P0 minus P, that is equal to, we will have 1 upon Vm into C plus C minus 1 upon Vm into C into P upon P0. So this expression is our BET equation, and this BET equation can be proved experimentally also, and from the experiments the left hand side of this equation can be obtained, that is this P upon V into P0 minus P can be obtained, and this can be plotted versus P upon P0. So this expression is in the form of Y is equal to mx plus C. So when we plot Y versus P upon P0, then it will give us a straight line whose slope will be equal to C minus 1 upon V Vm into C, and the intercept will be equal to 1 upon Vm C. That is when we plot a curve, that is when we are plotting a curve of P upon V into P0 minus P versus P upon P0, we will get a straight line, and the slope of this straight line will be equal to C minus 1 upon Vm into C, and the intercept, that is this intercept, it will be equal to 1 upon Vm into C, and these things are proved experimentally. Okay, and there is one limitation of the bed isotherm, that is so in most of the experimental cases we are getting a straight line, but whenever the pressure, that is pressure P, it exceeds the, or it exceeds the 1/3, or it is exceeding the 1/3 of the liquefaction pressure, at that time we may not get the straight line, and this is one of the limitation of the bed isotherm. Rest all the cases for, or rest all the cases where P is less than 1/3 of P0, this equation holds very good for all the adsorption isotherm, and experimentally also this relation is proved and it holds very good. Hope the derivation and the bed adsorption isotherm is clear. Thank you very much.